okay, wave propagation, because if they wanted to send and receive, they needed to the channel through the frequency. Frequency is very important for the communication system, so this is why we're gonna have to do. So today we're gonna the information measure for today, and also if we have time, the channel capacity or channel capacity. That is the zero bit the error rate under the specific conditions, and also the ideal communication system. That is also we're gonna learn about the topic. All right. So the informations sent to from digital sources when the date message is transmitted is given by, that is for the formula equation for information. The unit was bits, okay, bits. So keep in mind the base is not the 10, it was 2. So the log sub 2 of the 1 over the p sub j. So p sub j is probability of transmitting the j's message. So from the equations, we can find the relationship between the informations and the probability of the value. So the less likely to occur the probability, that was provide the more the information. Okay. So low transmitted the message means that was the more information. Okay. So information's measure depends on the likelihood sending message and does not depend on the possible interpretations of the contents. Okay. So it means we can measure is like how many the qualified to is able to recover the signal. It was not a big deal for this, the only information, the number of the information measurement. So and also, we can I sub j was informations recalculated the base on the 10. Okay, so log sub 2 over 1 over p sub j right there, and then p sub j, that was 1 over p sub j minus 1 p sub j. Okay, minus p sub j minus 1 front of the log. So and also we're gonna replace of the log sub 10 like this one. Minus log sub 10 p sub j over log sub 10, the 2. So after calculations, right there, like this, minus 3.322 log sub 10 of p sub j. All right. So to measure informations, we have to know about the entropy, means like average information measure of these resources. So the entropy as equations could be described as summation from j is equal to 1 to m. Okay, m is the number of the different message that can be sent. And that was I sub j we learned before informations times likelihood, the probability p sub j. Okay. In here, we assume that p sub j is equal to 1. Okay. For example, 1 over 3 plus 1 over 5 plus let's say 5, 3, 5, 3, 8, 7. So that should be is 1. Okay. So really fundamental property of a probability distributions. Okay. So the I sub j we learned before, log sub 2 of 1 over p sub j bits. Okay. And also the source rate, it could be the given by, it's very important. R is the equal to 8 over t bits per second. Okay, because the t is the period, second, h is entropy. Entropy is the average information. So beta sources is the bits. Okay, that is what I wanted to do. All right. Very simple and simple questions from the books. Okay, so find the information. So the information, when you see any questions from test or quiz information, you have to keep reminding, okay, this is the I. This is the I, okay? So the message that consists of the digital word, the 12 digital long word. Okay, so in which each bit is the digits, make it then on one of the per possible levels. One of our per possible levels, okay? So the probability sending any of the 4 letters, what that means, each message has 4 maybe options to be sending, and that what should be we assume that the equal level any does not depend on the value taken on by the previous digit. All right, so that is the kind of solutions for the previous question, the example 2. That was the possible combinations is the 12 digits. I mean the possible. So the possible combination is like 4 to the 12, 4 to 12. But we assume that each level is equally likely, or different words are equally likely. So the p sub j, that was 1 over 4 the 12. Go back to the equation, okay? So let's say that was for definitely we can rewriting 1 over 4 to the 12. Okay. So the informations that was 1 over piece of j, that was the equation. So this is y, 1 over 4 to 12. And then, we're gonna just like 4 minus 12 for the 12, low sub 2, for 12, it's the 12, low sub 2, and 4 is the mass. So the after that it was the 24 bits. Okay, so 24 bits. So this is the entropy, the average information, what we wanted to do until from the 1 to the m's combination. So we learned before that was the number of positive message is 4 to the 12. So 1 over 4 times the 12 multiply the 24. Because we have already calculated, that was we had already know from the previous one. And that was summation from the 1 to 4 to the 12. So that was finally 4 to 12. So times 1 over 4 to 12. So finally we got 24 bits. Okay. All right. So this is the another sample to understand information measurement. So the telephone, touch tone, keypad as these are 0 to 9 plus star and sharp keys. Okay. And assume that the probability sending sharp and star is probability, kind of likelihood 0.005, and probability sending 0 to 9 is like 0.009. So if the key pass rate, the 2 keys per second, compute the data rate of these sources. So the question is, we have to calculate the data rate for these sources. So the first over the data rate, that was R bits per second. That was what? H over T, H D over T. So means if we wanted to the data rate of the sources, we have to know the entropy, we have to know its period. Second. Okay, now, first over, that was formula equations we learned before in the previous relations. That was the 10, the times probability 0.099 times log sub 10, 1 over 0.009, right there. 0 to 9, 10, probability 0.009, 1 over 0.009. And that was piece of I maybe as well, but that was the 10 number, 0 to the 9. Maybe how about this one? Star and sharp. 0.005 is the probability likelihood. Definitely write this one. So after, just simplify the calculation, finally, average information, H is the equal to 3.38 bits per key. Okay. So the T is 1 over the 2 keys per second. That was the period. And, this is the reverse, the 0.5 second per kiss. So here, T over the H, 0.5 second per key, 3.38 bits per key. Key is right there, final 6.76 bits per second. Because the data rate, is R, was the unit is bits per second. So again, we have to find the R unit bits per second. To find the bits per second, the first of all, we needed to the H and T. So, okay. All right. So the channel capacity and ideal communication systems. All right. Let's say, uh, for digital communication systems, the optimum system that could be defined, well, we can define a lot of the meaning, but could be defined as the system minimize the probability bit error, the output system subject to constraint on the energy and channel bandwidth. Is it possible to invent a system with no error at the output even when we have noise introduced in the channel? Yes, but it should be under certifying the assumptions. So according to Shannon, he was, I think he was mathematics scientist, but according to the Shannon probability, error approach to the 0. But if rate of information, rate of data, R should be less than the channel capacity, okay? So if the R is less than the C, yes, it's the 0, the capacity. So right there, again, this is the formula H over T. C is B, the bandwidth, log sub 2, 1 plus S sub n, okay? Plus S sub n. The S of n, S over n, that was the signal to noise ratio. The B was the channel bandwidth, and the larger bandwidth as the more noise introduced to the system. It's kind of a trade-off. All right, so that is again, but that was in the analog communication systems. The optimum system might be the defined, the one of that achieve the largest signal to the noise the ratio at the risk of the output. subject to design constraints such as channel bandwidth and the transmitter. So the question is it possible to design infinite SNR ratio output when noise introduced by the channel? No, because Nyquist theorem, we'll learn for the future, Nyquist theorem. If the pulse represent 1 bit of the rate, non-interfering pulse can be sent over the chain no faster than the 2 bit. Okay, it's right there. That is the dimensionality, the theorem for digital signaling. We'll learn for the future more in detail. All right. So this is the sample questions for the example 4. We evaluated the channel capacity for a tele printer channel that has 300 hertz bandwidth and on SNR the 30 dB. So from the questions, we can assume that there was B 300 hertz and S over N, that was the dB. The unit was the dB. It's the 30, the dB for this system. Okay. Now, so the channel capacity, that is what we wanted to do. That was the formula, log sub 2, 1 plus S over N. That was, we calculated B over log sub 2, log 1 plus N over S, N over S. Okay. So now, so S of N, the dB, that was for, sorry, N log sub 10 S over N. So means N over S over N dB. That was log sub 10 S over N. So right there, S over N was 10.2 over N dB. I'm over the 10. Right there. Okay. So in here, 10.2, 10, we have already, that was given from the questions, 30. Okay, so 10.2, 3. So that was for 1,000. So that was the 1,000. So in here, the bandwidth, okay, 300 hertz, log sub 2, log 1,001. Okay, so the final, the after calculation, that was the 2.99 to 10 to 3 bits per second. Okay. All right. All right. Um, change color. All right. The last questions. Um, maximum telephone line data rate. So the computer user plan to buy the higher speed modem, okay, for sending data on a low telephone line. Okay. So we need to give the informations for users. I mean, the seller, I mean the buyer, the which has computer user plans to buy a higher speed modem for sending over data. So the telephone line has signal to the noise, the ratio, SNR, 25, the dB here. And that passes audio frequency of the range of 300 to 3,200. So from this here, we can make bandwidth, that was hertz, 3,200 minus 300, 2,900 hertz. Okay. All right. So the question is, what is the maximum data rate here? Okay. Could be sent over telephone line when there are no errors at the receiving the end. No errors, the receiving end. We learned before in the previous slides to assumptions. Shannon capacity was the less than Shannon capacity. Yes, that was for with no error at the receiving end, even though interference at the channel. Okay, so step by step, the SNR, the dB was, we learned before, 10 to log sub 10 S over N, that was 25 dB. So maybe I'm going to skip the calculations, okay? So S over N, 10 to 2.5, that was 315, 16.2. Okay, so the channel capacity is the B log sub 2, 1 plus S over the N, and that was for 2,900 hertz, log sub 2, 1 plus 360.2. Just that was the calculation. I'm going to skip the calculation. That was 224,097 bits per second. This is the channel capacity right there. So maybe any the highest speed of modem for sending data below the 24 kilobits per second? Yes, it was no error. So for example, the 22 kilobits per second, yes, that is a really good choice. But however, maybe 32 kilobits per second, no, there is the adding to the error. That was not good options. It would not work. That was modem signal would not work on the telephone line. Okay. Yep, that's it. Thank you. Um, the other chapter 2, I'm gonna make it another video. Okay. Thank you. Bye.